The acoustic resonator is a type of transducer, a vibrational device that I initially developed in an early attempt to duplicate John Keely's weights and jars of levitation experiments. It was based on the principle of a speaker or subwoofer, where an energized solenoid interacts with a permanent magnet stack. About 25% of the solenoid fits in the space around the lower 25% of the magnet stack, allowing for the strongest electromagnetic interaction possible with this arrangement. Since I would be working with water and vibrations, I needed something that would be completely waterproof. So I began experimenting with 14-ounce metallic soup cans. The metal can structure acts as a resonant structure and vibrates at its own resonant frequency when tapped in the center of the can's bottom face. So the center point is where I superglued a stack of neodymium disc magnets. I then created a solenoid to fit around the lower portion of this magnet stack, the core which was usually made out of either copper or a PVC cylinder. One end of the cylinder was superglued to a wooden base. The can is then placed over the wooden base so that the bottom portion of the magnet stack fits directly within the precise center of the solenoid structure. The perimeter of the can's mouth was traced with a marker, which would serve to outline the placement of the superglue, which would secure the can housing to the wooden base. Doing this ensures that the magnet stack fits within the solenoid with no physical contact, which could result in friction and mitigation of vibrational movement. Once the glue dries, the device was ready for testing. Turning the can upside down, it would fit over suitable plastic or glass cups. However, in order to transmit the vibrations directly into the liquid medium, a sort of piston was needed. I call this the acoustic piston. It is a suitable length bolt with a thin metal disc glued to the tail end. The head of the bolt is meant to fit to the bottom face of the can, conveniently kept there by magnetic attraction between itself and the magnet stack on the inside of the bottom face of the can. An amplifier switching circuit modulated by a digital function generator, as shown in the following schematic, controls the resonator. Now we activate the circuit and sweep through the frequencies until we come to several resonant frequencies. The resonant frequencies, which produces the strongest vibrational response, is used and usually results in the successful levitation of the object, which was either an egg or a golf ball in the water-filled jar over which the resonator was placed. The resonator used in the acoustic lubrication experiments was developed by simply making this design larger, using a 6-liter pail and larger magnets. The resonator is then placed on its side, as shown, and glued to a wooden base. A wooden platform is then glued to the top of the structure in order to hold the weights. Now, an acoustic piston in the form of a thick, heavy bolt can be mounted to the larger resonator to increase the energy of the vibrations. But we must keep in mind that though it increases the strength and energy of the vibrations, it also lowers the overall resonant frequency of the system. Now, this design has not yet been maximized. Firstly, the metallic material at the contact point of the bolt is eventually worn down by the vibrations, which perforate the material along the crease, causing mechanical failure. I attempted to use a larger standard size trash can of the same material. However, the material is the same thickness as the 6-liter pail, despite being on a much larger frame. Thus, the vibrations produced are much louder and sharper rather than being deeper and more powerful. To improve this, a larger can with proportionately thicker material and a reinforced crease will be needed. With this adjustment, more electrical energy could be added and much larger weights moved before the structure once again reaches mechanical failure. However, the most innovative improvement to the resonant structure would be in modifying its shape. As discussed in previous videos, the primary limiting factor in harnessing acoustic energy macroscopically is the distortion of the vibrations into dissipating shock waves at the higher energy spectrum. But we now know from John Keely's work, as well as the studies of Tim Lucas of Macrosonic Corps, that modifying the geometry of the resonator can greatly reduce or even eliminate these energy mitigating shock waves, thus enabling far greater acoustic energies to be developed and sustained. This process is called Resonant Macrosonic Synthesis, or RMS. Please see my videos Wired for Anti-Gravity and Personal Levitation Vehicle for more in-depth info on RMS. The links and timestamps that mark the RMS discussion are in the description below. With the aid of computer simulation acoustic software, the goal would be to evolve from using Helmholtz type cylindrical geometries to more bulbous-shaped metallic cavities to function as resonators and to tailor them to block the development of shock waves at the desired energy levels. Once the correct dimensions are determined, an industrial-scale 3D printer could then be used to create the resonator to the exact specifications. The other main improvement involves the actuated coils and the electronic driving circuit. In this present design, the actuator coil is made from 3 individual coils, wrapped trifler style or in parallel, around a common axis. The only difference is that the coils are not added by connecting their ends in series, but rather by having parallel ends, with each of the 3 coils powered by a separate power transistor and capacitor transformer power bank for additive effect. The pre-stage driver transistors are driven by an optocoupler train, with the LED portions connected in series and activated by a function generator. Connecting the optocoupler in series in this way ensures that the separate transistors and the coils that they drive are activated at the same frequency and in phase. But of course, at much higher activation frequencies, the optocouplers would fare better being connected in parallel than in series to reduce the activation lag between one optocoupler and the next. Potentially, one could add more than 3 coils and activation circuits to pack even more electromagnetic power into the same space. Now, anyone knows that ohmic heating comes with the territory when activating coils with electrical pulses, and thus the coils need to be able to breathe and cool off, and may even need to be replaced. My first designs involved just gluing the mouth of the cans and the wooden bases, but an improved design would allow the removal of the coil when needed, as shown in the diagram. One final adjustment would be to match the electrical resonant frequency of the driving circuit with the mechanical resonant frequency of the metallic substructure. This will greatly increase the strength of the currents in the electromagnetic field, hence increasing vibrational strength. This could be done by making each coil a part of a tank circuit. The challenge would be in creating a high power variable capacitor for the capacitive elements of the tank circuits. This will be crucial in order to tune a real-world system, as each pale resonator will have a slightly different resonant frequency, though it will likely still be in a certain range. Further, as already mentioned, the added piston will also change the resonant frequency. The heavier the bolt, the more it will lower their overall frequency. And lower frequencies will generally be needed to move heavier masses. Thus, the function generator is used to cycle through various tones in order to pinpoint the real-world frequency, which can't be predicted exactly by calculation. Once this frequency is reached by sound and feel with a function generator, the variable capacitor will then be used to further tune the system and to maximize vibrational power. A resonator operating on similar principles can also be made using a homogeneous metal pan or disc. This method is more stable and could support heavier weights than the pale version. In this design, the pan must have flaps over which to place the load-bearing posts as shown in the diagram. The pan should then be turned upside down, as this allows the structure the freedom to vibrate, as it is not constricted against the ground. The two posts are glued atop the opposing flaps and are the load bearers, and thus will not interfere with their vibrations. The horizontal baseboard spans and is glued on top of both of the posts. The solenoid is then glued to this baseboard bridge to fit over the magnet stack and then energized to produce the vibrations. Like with a pale resonator, there are multiple resonant frequencies, but one of the lower frequencies generally produces the better results. I've achieved up to 60% friction reduction using the pan resonator, and was even able to push over 500 pounds with several fingers, albeit still with some effort. But I am confident that many improvements could be made to the disc resonator, as well as being able to scale it up. In the next video, I will discuss the recognition of acoustic vibrations as a potential and viable source of energy and motion, and apparently even magnetism and gravity. It seems that more and more information is coming to light that is validating John Keely's claim of overcoming friction and even gravity by liberating the tremendous latent energy in all matter via sympathetic vibrations.